Welcome back everyone. In this lecture we will continue with the representation theory of SL2. So, first we will actually define some concrete examples of SL2 representations, and then later we will see that how to approach the representation theory of SL2 in a more abstract way. So, let us start with this following example. Okay, so we have this SL2. So, recall that we will simply denote it by SL2 itself, because always our ground field is assumed to be the complex numbers. So, this is spanned by these three elements Cx, Ch and Cy. So, note that the commutator relation gives xy is h, hx is 2x and then hy is 2y. Okay. So, now what one can do, one can actually take the space of homogeneous polynomials of degree m. Okay. So, take this Sm. So, this is the space of homogeneous polynomials of degree m. So, then it is clear that this is indeed spanned by the following polynomials. Let us say the polynomials in the variable t and u. Okay. So, then this is spanned by t power I, u power j, such that I plus j is exactly equal to m and I j are greater than or equal to 0. Okay. They are non-negative integers whose sum is m. So, if you want to write it very explicitly, so this is spanned by, so u t power m t into u power m minus 1 t square u power m minus 2 and so on t power m minus 1 u power m. Okay. The sum of these monomials will be a homogeneous polynomial of degree m, and the space of homogeneous polynomial of degree m is given by this. So, now you can easily calculate the dimension. So, because you can see that there are actually starting from if you consider only the power of u. So, sorry, this is supposed to be m minus 1 and u m minus 2 u square. So, it starts from 0, 1 up to m. So, that means we have m plus 1 vectors inside Sm. So, the dimension of Sm is m plus 1. Okay. So, now what is the action of SL2 on this Sm? So, I can write down the formula. So, the x acts on given any p, okay, for any p inside Sm. We have x acting on p is given by t times dou p divided by dou u, and then the h acts on p given by t times dou p divided by dou t minus u dou p divided by dou u. Okay. And how the y acts? Y acts on p given by u times dou p divided by dou t. Note that the action of h can be obtained from the action of y. So, we need to have that this is exactly y acting on p, like x y acting on p minus y acting on x p. Okay. So, using this formula one can actually calculate this formula, that is not a problem. Okay. This formula can be obtained using this. So, now I will leave it to you to check, it is a routine exercise to check that using this action we have the following formulas. Okay, this is check. Indeed, this gives you sl2 action. So, this gives sl2 action. How to check this? So, basically you need to check that x h acting on p is same as x acting on yp minus y acting on xp. So, that is the first formula. The second one, 2 xp should be exactly equal to h of xp minus x of hp. Okay. So, this corresponds to the bracket xy is equal to being h. This corresponds to the bracket hx being 2x, and similarly, so the one last one corresponds to hy being minus 2y. So, that means minus 2yp should be equal to hyp minus yhp. Okay. So, these formulas one can check directly. So, this is direct computation. Okay. But what is interesting indeed, if we take for example, this particular type of basis. Okay. So, we are taking some modified basis. Okay. So, then we have these following formulas using that basis. So, we take t power m and then m times t power m minus 1 u, then m choose 2 t power m minus 2 u square and so on, then m times t times u power m minus 1 and then u power m minus 1. So, you take all these elements, there are m plus 1 elements. So, you know that this is just a constant multiple of the earlier basis. The earlier basis is just t power m etcetera u power m. Now, we have adjusted the constant, so that it will become very clear how to write the action of h, x and all. Okay. So, now you can actually directly check. So, on this basis we have the following action. Okay. So, the action is very explicit here. So, let me write down. For example, I can actually compute it for some particular case. Okay. I will leave it to you to check the remaining formula. Okay. If I take h, so let us call them w naught etcetera w m. So, this you call it w naught, this is w 1 and so on, then this you call it w m. So, basically the uth power, that the label that we are using. Then it is easy to check h w I is indeed m minus 2 I w I. Okay. So, and if you take for example x w I, so that is going to be give me m minus I plus 1 w I minus 1, and you just take w minus 1 to be 0 here, because x w 0 is going to be 0. And similarly, y w I, that is given by I plus 1 w I plus 1, and again here we set w m plus 1 to be 0. Okay. So, these formulas again can be verified directly using the action of h, x, y on this homogeneous polynomial. So, let me just verify the very first one. I will leave it to you to check remaining thing. Okay. So, what is the action of h? So, recall h is given by t dou p by dou t minus u dou p by dou u. Okay. So, let us recall h is p is t dou p by dou u minus T dou P by dou T minus U dou P by dou U. T U dou P by dou U. So, now for example, if you take some typical element ith term. So, how W I looks like? So, W I looks like M choose I, okay, M choose 0 is 1 and M choose 1 is 1. So, remaining things are M choose I and then T power M minus I, T power M minus I, U power I. So, this is the typical term. So, now if you compute this, you can see that dou W I divided by dou T is going to be M choose I M minus I T power M minus I U I. So, then you are going to multiply by T. So, then the power will be increased. Then you want to subtract, okay, this is the action of H on W I, that is what we are computing. Then we want to subtract U dou P by dou U. So, that is going to be minus again M choose I. So, I times T power M minus I. So, U power I minus 1 will be there. So, that is going to give me, so yeah, M power I. So, this plus 1 is not there because we are differentiating. So, this is T power M minus I, U power I and then here again M minus I, U power I. So, now this is gives me H W I equal to M choose I, you take it out and then this is M minus I minus 2 times T power M minus I, U power I. So, that is exactly M minus 2 I, which is H W I times W I. So, this is what we wanted. Okay. So, if we take this H W I which acts on this W I as M minus 2 I W I. So, from this you can see that entire action of SL2, how it is acting. Okay. So, these formulas are very important. So, we will actually make some important observations using this formula. Okay. So, these formulas are easy to check, they are just plain computation, that is what I did here for H action. Okay. So, I will leave it to you to check what is this. So, let me just recall these formulas and then let us make some observation using this. So, H W I is given by M minus 2 I W I. So, that means each W I is an eigenvector for H. Okay. So, this implies W i's are all eigenvector for the action of H. Okay. Not only that, what is the eigenvalue? With the eigenvalue M minus 2 I. Okay. Note that this I is actually ranging from 0 to M. So, that means when you put 0 here, it gives me M. So, the eigenvalues are starting from M and then goes to M minus 2 and then all the way it goes to minus M plus 2 and then minus M. Okay. So, these are all the eigenvalues. For example, W0 is the eigenvalue corresponding to M and then W1 corresponding to the eigenvalue M minus 2. So, these are all the H eigenvalues and these are all the H eigenvectors. Since all these eigenvalues are distinct, we can easily see that all the eigenspaces are one dimensional subspaces of this SM. So, then this is corresponding to M minus 1 and this corresponds to WM. Now, how the action of X and Y can be understood. So, X W I is going to give us M minus I plus 1 times W I minus 1. Okay. Similarly, Y W I gives me I plus 1 times W I plus 1. So, now using this formula one can see that, let us use different colors. So, now the x action, like let us say x action, let us try to understand. So, it pushes, okay, if I take wi and then it actually pushes down one script, okay. Basically, if I apply x on w1, then it actually takes here, okay. Similarly, on w2, if we apply, then it takes here, so and so on. So, it is basically x pushes down indices by 1, and of course, up to multiple of w i's, okay. The multiple is not important, because everything is one dimensional, where that one dimensional space is pushed, that is what we are seeing. So, when you apply w I x on w I, then it takes to w I minus 1, that is the important thing. Now, let us see how the y action actually plays the role. So, if we take this w I and apply y on that w I, then it actually pushes this w I to w I plus 1. So, that means w I minus 1 is mapped to w I, and then w I is mapped to w I plus 1, up, of course, up to scalar. So, this is the y action, okay. So, y actually pushes up, and then x is pushes down, okay. And h, what it does, h is actually, all of them are eigen vectors. So, it actually just applies it as like a loop, okay. So, this is the action of h. So, it maps to itself, okay. So, this is how the SL2 action is actually understood on this module SM. Now, using this, what one can conclude, okay, one can immediately conclude that SM must be irreducible submodule, okay. So, here is the claim. SM is indeed SL2 irreducible representation, okay. So, first of all, let us define some notions, okay. So, here it is clear that this W naught, okay, when you apply x, it is killed, okay. So, note that h W naught is given by m W naught and x W naught is killed, okay. And if you apply y powers on W naught, you are able to actually get back entire thing, okay. The SM is indeed the span of y power j W naught, because y W naught is indeed increases, okay. Whenever apply y on W naught, you will go to W1, then if you apply y again, you go to W2 and so on. So, when you actually repeatedly apply y powers to the W naught, again you can actually just apply from 0 to m minus 1, because y power, sorry, we need to apply up to m. So, you can also see that y power m plus 1 W naught. So, that is going to be multiple of W m plus 1, okay. Every time you are actually increasing the index by 1. So, if you start with 0 and then go up to m, you will go to W m, and then m plus 1, you are going to go to W m plus 1, okay. So, that is going to be just 0, because you can see that y W m is nothing but 0, which is multiple of m plus 1, W m plus 1, which is 0, okay. So, now any vector that satisfies this condition, okay, that will be called what is called highest weight vector, okay. All the eigenvectors of H will be called weight vectors, and the corresponding H eigenvalue will be called weight of that vector, okay. So, let us make these definitions. So, definition, so this is true for any SL2 module. Let us say V is sl2 module, okay, any eigen vector of H is called weight vector, okay, and suppose the weight is, let us say V is the weight vector and weight is A. So, then A is called the weight of the weight vector V, okay. So, a non-zero vector W in capital V is called highest weight vector if whenever you apply H, it is going to give you some weight. So, let us say some A times V for some A in C, okay. So, let us say highest weight vector of weight A, let us fix that A inside C. So, then we should have that HV equal to AV and XV should be 0. So, we will see that we will see later that why it is called highest weight vector, because XV is being killed, okay, the weight of this by applying the sl2 action on V, we will not be able to get weight vectors which has weight more than A, okay. So, this is actually something that we are going to see, okay. So, basically what I am going to show. So, this is the fact which will be proved later. So, the weight of this sl2 module generated by V, okay, because I have defined already weight. What is weight? Okay. If I take a H eigenvector, the corresponding eigenvalue will be called weight. So, one can actually talk about weights of all this sl2 module generated by V. So, that will be the H weights of this module. Then one can prove if this vector has weight A, then this will be contained in like A minus Z plus. Okay, this is by definition A minus R greater than or equal to 0. Okay. So, that is why we call this vector V is the highest weight vector of weight A, because this is there is the total order on this A minus Z plus. A is indeed the largest element in this A minus Z plus. So, we will actually see that later, but anyway let us get back to our example. So, what we want to do, we want to prove that this Sm is indeed irreducible representation. So, to prove this, we need to see the following fact. Okay. Let us start with some submodule V of this S. So, this proof indeed will go through for any abstract irreducible module. So, we have to pay attention to this proof. So, let us start with V being a non-zero module inside Sm. Note that H is diagonizable operator, acting on Sm, okay, because Sm is direct sum of these eigenspaces. So, yes, H is diagonizable. So, now if you have any diagonizable operator, if you restrict that to any invariant subspace, that will be again diagonizable. So, H restricted to V is also diagonizable. In particularly, V can be written as direct sum of eigenspaces. So, direct sum of H eigenspaces. Indeed, this is direct sum of weight vectors. Okay. So, since H has the eigenvalue coming from m etc., okay, m minus 2 etc., minus m plus 2 m. So, this will be called string of H weights. Okay, this is indeed string because it is unbroken and starts from m and then goes all the way to minus m. Okay. So, string of H weights. So, indeed if V is direct sum of H eigenspace and V is non-zero, then we will be able to find a vector V inside V, and that vector will have weight of that V will be some m minus 2m, okay, for some I belongs to 0 to m. So, now let us look at that V. So, then this space spanned by this V has to be exactly space spanned by W I, because they are one dimensional spaces. The eigenspace corresponding to m minus 2I is one dimensional. So, this has to be equal to this. So, that means if I take this space spanned by this is going to be inside capital V. Now, go back to our diagram, you can see that. So, Wi is going to locate somewhere here. Okay. So, then if I take this Wi, if I use for example the action of x, so then the action of x is going to bring the thing down, and if I use the action of y, so it is going to actually increase, it is going to increase the index. Okay. So, that means by repeatedly applying x and y, we will be able to reach other wj's. Okay. So, by applying x on wi, we will actually again we will get some scalar multiple of wi minus 1. Similarly, by applying y, we will get scalar multiple of, again non-zero scalar multiple, that is more important. Okay, non-zero scalar multiple of wi plus 1, that is in V. Now, by repeating this we get that. So, by applying various powers, okay, by applying various powers of x and y, we get all wj inside capital V. That shows that Sm is subset of V, that shows that Sm equal to V. Okay. So, this proves that indeed the module that we have constructed is irreducible module. Okay. And note that there exists some vector up to scalar multiple such that the H eigenvalue of that or the H weight of that is m, and m is the largest weight among all the weights. Okay. The weights of this Sm, which is all the H eigenvalues, okay, weights of this Sm is given by this string m minus 2 etc. minus m plus 2 minus m, and m is the largest weight or maximum weight. Okay. So, in particularly this W naught is the highest weight vector, and it is unique up to actually constant multiple. Okay. So, it is indeed exercise, I will leave it to you. W naught is the only highest weight vector, of course up to scalar multiple, inside Sm. That means, if you have another vector V which has let us say highest weight A, then this V has to be multiple of W naught and that A must be m. Okay. So, what we need to prove? So, you need to prove that if V is inside Sm, which is Hv equal to some Av, and xv equal to 0, then that implies A equal to m and v is inside the span of W naught. Okay, this is the thing one needs to prove to say that it is the only highest weight vector up to scalar multiple. Okay, this gives actually for any given non-negative integer m. So, you have this Sm which is actually irreducible module. Okay, given m in Z plus, we have this Sm, so which is sl2 irreducible module. And we will prove that this correspondence is indeed one-to-one correspondence between Z plus and the isomorphism classes of irreducible, finite dimensional irreducible sl2 modules. So, our main theorem, so let me state it here. So, this map call it phi is from Z plus to the set of all isomorphism classes of sl2 representations of finite dimensional irreducible sl2 representations. We have this one-to-one correspondence. The map is given by just m goes to this Sm. So, this is how we denote the isomorphism class corresponding to Sm. Okay, so this is the indeed main theorem in the theory of sl2 representation theory, finite dimensional theory of sl2 representation theory. So, then we have this actually the theorem of while. Okay. So, here is another theorem. So, let us call this theorem 1 and then this is theorem 2. So, this is while's complete reducibility. So, that says any finite dimensional sl2 representation is completely reducible. So, completely reducible. So, that means as a corollary, like any representation of finite dimensional representation of sl2 can be written as direct sum of these Sms. Okay. As a corollary, if V is sl2 finite dimensional representation, then there exists, let us call it k1 etc. some kr positive integers such that okay, and m1 etc. mr which are non-negative integers such that V is indeed isomorphic to Sm1 direct sum k1 direct sum Sm2 direct sum k2 direct sum etc. direct sum Smr kr. Okay. So, these are all the only finite dimensional representation that you can get it for sl2 representations. So, sometimes actually people use V of m to denote this Sm, okay, up to isomorphism actually they are isomorphic. So, this V of m indeed constructed using some abstract approach of representation theory, but anyway. So, this is also used for denoting irreducible sl2 representation corresponding to the non-negative integer m. Okay. So, this is what actually for example, Humphreys uses or Anderson uses. Okay. So, this is used in Humphreys, even Anderson, etc. Okay. We will also use this notation in coming classes. Okay, so these are all the main theorems that one needs to prove for in the SL2 representation theory, and we will actually prove these theorems in the next classes. Okay, first we will actually classify all the finite dimensional irreducible SL2 representations, and then later we will prove actually the complete reducibility for SL2. Actually, the proof that I am going to give for SL2 complete reducibility of SL2, that may not actually go through completely, like one may not be able to generalize it as it is to the general SLN or finite dimensional simple algebras. But to get more closer look at SL2 representations, I want to actually give this proof. Okay, so that is going to tell you like how one can in general approach representation theory. Okay, so I will stop here and we will continue with the SL2 representation theory in the next class. Thank you.